going to do today in the next 90 minutes is I'm going to tell you that you should completely change the way you think about computation. Okay? Let's see how far we get with that. So here is a very, very first computation. That's the one you shouldn't change the way you think about at all. This is perhaps sort of maybe one of the easiest kind of computations, and you learned how to do this in elementary school, not even in high school, right? It's division with remainder. And I'm not going to talk about how a computer does this. You just think about how you do this kind of computation. So here are two numbers, 23,736, and I would like to divide this by 736. Just by the size of those two numbers, you already see that there should be 2 digits before the decimal point. And then you all know how this works, right? So you check how often 10 times this fits into here. It turns out 3 times. You write down 3 times 736. You subtract it from each other. This is the remainder. Now you check how often 1 times this fits in here. This is 1,472. You subtract those two numbers. This is the remainder. Now we know that the number has to start with 32. And then we check how often 0.1 times this number fits into 184. It fits 0.2 times or 2 times. That's this number. Oh, and you're left with something which just happens to fit perfectly into 736. You just multiply by 5, and you're left with a remainder of 0. Okay, that's boring, but there's something interesting about this kind of computation, and that is that while you're performing it, you could just stop at any point, for example here, and you know what you know, and you know what you don't know. You know that these two numbers are not going to change anymore, no matter what's going to come afterwards. So you know how precise this kind of computation is, and what the error could possibly be on this kind of computation, right? So the kind of computations you do in machine learning don't have this property. They are quite different. So here are a few examples. Or everyone's favorite example nowadays. If you train a neural network, let's say with stochastic gradient descent on your big data set, and you do 4 steps of stochastic gradient descent, how close are you to the true optimum, to the true perfect performance of this neural net? You don't know, right? Nobody knows. Or if you run it for a lot longer, but you don't use the entire data set, you only use 1% of your data set, how close are you going to be to the performance you could get if you use the entire data set? It's quite a difficult question. It's perhaps not impossible to answer, but it's very difficult. But it's not just neural networks, right? I don't just want to bash neural networks. You just had a wonderful lecture on Gaussian processes. If computing the posterior on a Gaussian process involves inverting a matrix. Let's say I'm deciding to invert this matrix with the backslash operator in MATLAB, or sort of the most elementary kind of computation, that's Gaussian elimination. But I'm not going to actually run it until it converges, until it's finished. I'll just start it, and then I'll just stop it at some point. How good's the answer going to be? You don't know. This also works for more complicated models. So for really complicated, big Bayesian non-parametric models that Tamara is going to tell you about on Monday. She's sitting in the back row, by the way, now, making me nervous. So how do you do marginalization in a big graphical model? You do MCMC. That's what Zubin told us, right? Let's say we run our MCMC sampler for 20,000 steps. How representative are those 20,000 numbers of the true distribution? You don't know. Why is this a problem? The problem is that we use all of these methods, and then we string them together into one big pipeline, and then we call that our machine learning system. And these things used to be the kind of stuff that tells you what kind of ads to show on Facebook. Great. But nowadays, we're talking about using these methods to build together big controllers that drive cars autonomously, that make trades on the market for you autonomously, all these kind of really dangerous kind of things. And now people are getting worried that this kind of AI is going to become a problem for our society. And most of the time you read about these kind of big AI questions, people are worried that their toaster is going to become self-confident, sentient, and try to kill them, right? I don't think that's what's going to happen. I think a much, much bigger problem is that we can't rely on these methods to actually do what they're supposed to do. So quite often they just don't work, and we don't know why they don't work. Why is it so hard to do these kind of computations in machine learning? Well, it's because our computations we have to perform are really challenging. They're not just division with remainder, right? They are typically intractable kinds of mathematical computations. And here are some examples of these. I think these are the 4 most important classes of intractable numerical mathematical tasks we have to solve when we use machine learning methods. We have to do perhaps the most elementary kind of computation, linear algebra, as I just mentioned, for GPs and least squares, and sort of the really elementary kind of fitting. We have to use optimization methods for any kind of nonlinear training and fitting, for neural networks, for example, but also for SVNs and various other kind of models. For everything probabilistic, whenever you have to marginalize over some latent parameters, you have to integrate over them. That's an integration problem, and we often solve these with MCMC methods or various other techniques or approximate inference. And whenever you're dealing with some kind of dynamic description of the environment around you, if you have to predict what's going to happen in the future and you think it's going to be something that depends on where you are now, but it's not just where you are now, then you have to solve some kind of differential equation. Often it's just a linear differential equation and then it's essentially linear algebra, but sometimes it's also a more complicated problem, right? So at the moment, when we solve these kind of tasks, we solve them with black boxes. We solve them with classic numerical methods that we take off the shelf. I'm sure some of you have written this in your paper. We are using an off-the-shelf solver to solve this particular problem. And why are we doing that? Well, because these are methods that have been developed by a different community, by other people, by numerical mathematicians, by the operations research community for optimization maybe. And we trust these people that what they are doing for us works, that they are just doing the right thing for us. And if we ask them how they are solving these kind of problems, they say, it's none of your goddamn business. Right? So you're assuming that this is exactly the right thing to do. I think this is a good approach if you want to be a data scientist. If all you care about is your data and how you think about your data, and the rest should just be something automated that runs on your computer. If you want to be a computer scientist, you have to think about those computations and understand what they do for you. And once you start thinking a little bit about what these methods do, the first thing you notice is that they're actually machine learning methods. So what does a numerical method do? A numerical method estimates something you don't know, given something you do know. It estimates the result of an intractable computation, given the result of a tractable computation. It estimates a latent quantity, given an observable, where the observable is the result of a computation. In fact, they are actually active learning machines, because they are performing the computations themselves. They decide what kind of data points to collect. So for example, an integration method is a method that estimates this object, the integral, given evaluations of this object, the function. Or an optimization method is a method that estimates the root of some gradient, I'm simplifying a bit here, given evaluations of that gradient at various points that aren't the root. Right? So in this sense, all of the methods I had on the previous slide are statistical estimation rules. They are active machine learning algorithms. So that kind of observation is not new. It was made several times by many people. The first proper paper I know is by Percy Diaconis in 1988. Neil will point out that there's also a very good paper by Tonio Hagen 4 years later, maybe even a year earlier, I don't know. Percy claims that Henri Poincaré was aware of this in 1896. I've tried to find the corresponding sentence in this book. I couldn't, but maybe my French was just not good enough. So it's definitely an idea that has been pointed out several times. You can also find it in textbooks, like in David Mackay's textbook, for example. Zubin Naramani has written papers about this in the early 2000s. But it's mostly just been pointed out as kind of a quirky connection. It's kind of, well, it's kind of the same thing, really, computation and inference. But it's never really led to a concerted community effort to do something with this kind of insight. And the reason for this is, I think, not mathematical. The reason is a community problem. Numerical mathematicians don't use statistics, and they don't like statistics because it's kind of a dirty subject, right? It's not hard maths. And statisticians have a real problem with applying their methods to something that is decidedly not random. That's the tricky part here. All these problems are fundamentally not random problems. They're typically totally deterministic. And I'll tell you more in a second what I mean by that. But from a probabilistic perspective, if you're talking about inference using probability distributions, there's no difference between uncertainty arising from randomness, aleatory uncertainty, and uncertainty arising from lack of information, epistemological uncertainty, or epistemic uncertainty, sorry. Okay, so what does this mean? It means that it should be possible to compute, just like it's possible to compute probabilistic versions of statistical estimators, it should be possible to construct probabilistic numerical methods. Methods which take in a probability measure over the task they are supposed to solve, over all the variables that describe the task, and return a probability measure over the outputs of this problem, such that this posterior or output probability measure somehow quantifies the uncertainty arising from the input and the finite information content of this kind of computation that they are performing. That's just what should be possible. And I'm going to talk today about to which degree this is possible and why this is hard, why it's sometimes easy, and what kind of surprising insights you get from this. So over the past 4 years or so, some people, including myself and my research group, have been trying to address this problem and make it mathematically more kind of graspable. Not such a vague philosophical statement with just words, but something that actually contains formulas and mathematics. And some of the most important results we've found are that there is a precise mathematical connection between certain interesting classic numerical methods and certain interesting classic statistical models. That you can describe one as the other. That allows us to build some kind of scaffolding for a theory of probabilistic numerical methods and sort of study these classic methods as examples of why certain things are hard and how they can be solved. So for example, it was known when we started, thanks to Percy, that in quadrature there is a direct connection between classic quadrature rules and Gaussian process regression. I'll talk about this for almost the entire talk today, because it's a very nice, simple connection. But we've now also been able to show that in linear algebra, there is a close connection between the conjugate gradient methods, and I'm going to show another example of that on Monday, and certain parametric Gaussian conditioning or Gaussian inference rules. In nonlinear optimization, there's a connection between quasi-Newton methods, which Steve Boyd mentioned on the side as something you shouldn't worry about, and autoregressive filtering rules. So that's the thing that Neil just talked about, and that's what you should clearly care about. And more recently, we've also been able to show that in the task of solving ordinary differential equations, there's a direct connection between Runge-Kutta methods and certain Gauss-Markov inference rules. This is just vague sentences now. I'll show you what I mean by that in a second. So we'll start with exactly this kind of first problem, and in fact, this is going to be the entire next hour. So integration. This is the task of computing this number, which is the integral over this function f of x over some domain, given the ability to evaluate this function more or less wherever we like. Okay? And because I don't want to be so abstract, I'm going to show you a very concrete example so that we have something to think about. It's this function, and I'm going to write it on the blackboard as well so that it doesn't vanish once I move this slide. The function is f of x. X is a real number, and the output of this function is also a real number. It's the exponential function of minus the sine squared of 3x minus x squared. So the first thing you notice about this function is that it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 symbols. It's this wide on the blackboard. And I can evaluate this function on this computer for any double precision value of x in about 10 nanoseconds. I tried. The reason I'm telling you this is clearly a deterministic object. There's nothing random in here. There's no random number. There's no sampling, right? There's no generative model. That's the function. However, if I write an integral sign in front of it from -3 to 3 and call this the real number f, even though this number clearly exists, you don't know what that number is. Right? Nobody in here can tell me what that number is, simply because this function is not in any tables of integrals that you can look up. I've checked. Right? So clearly you are uncertain about this thing, because if you were certain about it, you could tell me what it is. Right? You don't know what it is. You are uncertain. That's the most important part of this entire talk. And if you were sort of, I don't know, various incarnations of leading statisticians, you could have an entire week-long debate about whether that makes any sense or not to say, are you uncertain about this number? But clearly you are, because you don't know, right? It's easy, though, to bound this number, because this function is strictly positive. So the integral over it is strictly positive. It has to be a number larger than 0. There's also a simple upper bound to this function. Can someone see what the upper bound is? 6 is a good upper bound, yeah. There's a slightly better bound. So 1 is a good upper bound. Let's look at this expression here. So sine is a number between -1 and 1. Sine squared is a number between 0 and 1. This is like the exponential of a number between 0 and 1 times minus the exponential of minus x squared. So it's a number less than 1 times e to the minus x squared. So this function is upper bounded by the Gaussian function. Right? You know what the integral of the Gaussian function is? It's the square root of pi, a little bit less than the square root of pi, if there were no integration limits here, right? So clearly this number has to lie between the square root of pi and 0, or 0 and the square root of pi. Okay? Good. That's not enough. We want to have a more precise answer. So if you wanted to compute this number, the integral over this black line, what would you do, given access to this computer? But not access to MATLAB, no access to numerical libraries, right? Just elementary computations on a computer. Symbolic integration requires, I don't know, Mathematica or whatever, right? And actually, it won't give an answer. I've tried. You could divide it up. That's one option. What did Zubin tell you to do on Tuesday? MCMC, sampling. It doesn't even have to be MCMC. It's enough to do just MC, because you can sample from this distribution. Right? I can sample from the red curve. Here are a bunch of Gaussian samples. I know how to draw Gaussian samples. Well, actually, you could argue whether that's acceptable on a computer. But let's say we have access to something that produces uniform random numbers, then you can produce uniform Gaussian random numbers from it. Now, for each of these random numbers, I could evaluate the ratio between the red curve and the blue curve, and then multiply this ratio by the known integral over this upper bound, which is something like the difference between two error functions, and then sum up all those ratios. And what do I have now? I've got a random number f hat, which is a statistical estimator for the true integral. And then you can go ahead, if you're a good statistician, you can check properties of that random number. For example, you can show that it's unbiased. That's a good thing for an estimator, right? You can also show that the error between the true integral over this function and the estimate, this f hat, this random number, the error is the square root of the variance for me. That drops like 1 over the square root of the number of samples I've drawn. So the variance drops like 1 over n, and the square root of that drops like 1 over the square root of n. That's a wonderful property because this is called the min-max optimal weight for unbiased estimator, so it's a really good statistical estimator, right? This is the right way to compute this estimate. And up here I've shown you how this runs. So this gray line, that's one particular Monte Carlo run. The first few points here are those. And then after that there's just lots and lots and lots more points. And this is sort of how this goes down. And these gray lines, these are instances of constant over the square root of n. Okay? So that's how you can compute an integral, and it's a perfectly valid way to do this. So now you could say, I don't have to deal with this anymore. This works, right? I've done this way. It's none of your goddamn business how I did this. This is the number. Okay? So, yes?
But why did you sample this without nothing?
That's a very good point, right? I could also draw from a uniform distribution. Thank you. I could also draw from a uniform distribution. It totally works as well, right? So this is now a different function that I know how to integrate. There's a different constant up here because this g that I'm drawing from is a different number, so the variance of this f over g is a different number. This just changes the constant. The rate doesn't change. That's this dashed line up here. So this particular proposal is a little bit worse, right? Because it's not so good a bound. You could do bits of big theory about what the minimum variance MC estimator is for this, and there's probably a different function that's even better than the Gaussian proposal, but it's not going to change the fact that you get this kind of stochastic convergence. Why? Because you're using random numbers. And if you're building a random number, like a random number that is a statistical estimator, which is unbiased, it'll at best converge like this. But that's not because this problem is hard. It's because you've chosen to use random numbers even though you didn't have to, because the problem is entirely deterministic, right? So imagine you sort of, a week ago, you had a bicycle accident and now you have amnesia. You just woke up on Monday morning and you came here and you just kind of listened to Zubin and Neil and various Bayesians telling you how to do Bayesian inference, and you forgot everything you learned in high school, everything in your undergrad elementary math courses on how to compute integrals numerically. How would a Bayesian estimate this unknown number, capital F? I'm not asking for an algorithm. I'm just asking for the general scheme, how to crank the handle. Yes, you need a prior. Well, actually, you need a generative model, which is a bit more complicated than a prior. What you need is you need a joint probability distribution over the things you get to see, the data, and the things you don't know, the latent variable, right? So you will need a joint probability distribution over all the f's that I could possibly evaluate, and this thing that I actually want to have. And then I can split this up into a prior and a likelihood, and I can perform inference, right? So I could write this as P of f given f times P of f, something like this, right? And then normalize respectively, get Bayes rule. Okay, so here I've chosen a particular joint probability distribution. It's my favorite joint probability distribution. Actually, it's just a distribution over f so far, over the little f. And it's also Neil's favorite probability distribution, and hopefully now also some of yours. It's a Gaussian process. Simply because it's the only real probability distribution that I know how to put over function spaces. like without actually just using a GP and transforming it. So it's also not just any old Gaussian process, it's a really cool Gaussian process that you just learned about this morning. It's the Wiener process. So it's Brownian motion, the thing that Einstein studied. Why? Well, because it's in some sense the most elementary, the oldest kind of Gaussian process. Einstein wrote about it. Clearly, it must be cool. Right? Let's just use this. That's not a good motivation, and we'll see that this bad motivation will have an effect. But I'm just going to use this. So there's a wonderful property of Gaussian processes that Neil already pointed out several times. Any Gaussian, joint Gaussian random variable has the property that any linear projection of this Gaussian variable is also Gaussian distributed. In particular, if our Z is this infinite dimensional object f, then the linear projection of this object f called integral, which is basically just a big sum, is also a Gaussian random variable or a Gaussian probabilistic variable, uncertain variable, with a mean, that's just a number, right? It says this is a univariate Gaussian distribution, a mean, which is the integral over the mean function, and a variance, which is the double integral over this covariance function from the left and right. You can do this with this covariance function, and it gives you this object here. So that's just a bunch of numbers you can plug in. So by defining a joint probability distribution over the function values, I've already defined a joint distribution over the function values and the integral, because it's directly implied simply by having a distribution over the function values. Okay, I'm not done yet. I need one other ingredient to build a probabilistic numerical method. The first ingredient was the generative model. The second ingredient is I need to know what numbers to compute. Right? Because, I mean, I have access to all of f, all the function values, but I haven't actually computed any yet, except for when I made this black line here. So which one should I choose? Exactly. So perhaps the ones that I'm most uncertain about, because they're going to give me the most information about what's going to happen. That's only, like, it's slightly incorrect, actually. Ideally, I'd like to use numbers which maximally reduce the uncertainty over this thing here. But in this particular case, this is actually the same. If you had a different covariance function, then things would be a little bit more complicated. So the most uncertain number is the one furthest to the right. That's this one. So I'm just going to evaluate this and condition on it. Nice. Now I have a new estimate for the integral, a new estimate for the function. And after that, now this number is the one I'm most uncertain about, so I'll evaluate here. And you see up here, these are the two estimates I just constructed. The fat red line. Now I'm most uncertain in the middle, so I'll evaluate over here. Good. So now I've stopped the animation because there are going to be more and more of these slides, and otherwise I would have 200 megabytes of slides on here. Now I'm most uncertain here and here, actually equally uncertain, so I could evaluate at both points. And now you see how this story is going to continue, right? So I'm just going to evaluate on a regular grid eventually. Right now I'll always bisect these evaluation points, and this thing will sort of converge. And ooh, wonderful! This performs a lot better than this Monte Carlo estimate. In fact, you can show theoretically that this thing converges like 1 over n squared. So in the log domain, it converges like 4 times faster in orders of magnitude, right? This is 1 over square root. This is 1 over n squared. Yes?
So doesn't this convergence rate depend on the dimension of the problem?
Yes, but this problem is one-dimensional.
In general?
In general, it's more complicated. But this problem, one-dimensional. The reason, no, this is an important point. There is one function I'm integrating, and that's the one function, right? I'm not saying, whatever your function is, do this. I'm saying, here is one particular problem, and let's say this problem is important for your PhD thesis. And you have to solve it really efficiently because this function is going to be called 10 trillion times in your C code. You're not going to use Monte Carlo integration because it's just not going to work, right? Of course, you don't have this function in your PhD thesis, you have a different one, right? But my point is, by thinking about the task you're trying to solve, you can come up with a method that can perform drastically better. So let's say we want to have sort of, I don't know, 10 to the minus 7 precision, maybe. Then I'll have to do something like 1,000 evaluations with this rule, and something like, I don't know, like several million evaluations with Monte Carlo. Okay? There was something else that was really interesting that perhaps sort of slipped past you when we did this, and that's that these posterior mean functions here, these straight lines, are straight lines. Right? So I'll show this again. Let's hang on. Here we go. This is the posterior mean function after 1, 2, 3, 4, 5, 6, 7 evaluations. So that's the posterior mean, and our mean estimate for the integral is the integral over this mean estimate for the function. sort of twisty in your head, but that's the property of Gaussians, that they're closed under linear projections, right? What's the integral over this function? It's a piecewise linear function, so maybe you can, like, in your head, think about how you would compute this integral, right? How would you do that? You could also write this integral as sort of a sum or a bunch of boxes. This box, this box, this box, this box, this box, this box, where each box has the average height of this trapezoidal part up here. Right? And then you can just write down what this thing is. It's just a sum over sort of pairwise averages of subsequent points. This is called the trapezoid rule, and I'm sure that every single one of you has seen this either in high school or at the very first year of your undergraduate math courses. This is what your high school teacher would have told you how to compute an integral. You evaluate on a regular grid, and then you do a Riemann sum, basically, right? So what we just discovered is that the trapezoid rule, do I have a statement for that? The trapezoid rule is a maximum a posteriori estimate under a Wiener process prior over the function f, where we've evaluated this function such that we get maximum information gain about the integral. So we've derived this totally classic rule in a completely probabilistic, sort of non-parametric machine learning way. We wouldn't have needed the theory for this, we just derived it in this way, right? And I can tell you that this same trick works for various other classic integration rules. So if you're now asking about Gauss-Legendre or Gauss-Seidel or all sorts of tricks that are more complicated than piecewise linear interpolation, they can all be written as kernel-rich regression or as Gaussian process inference, right? So doing this has kind of, we've now just rediscovered something that's like 100 years old, but we've got something new, and that's this slightly less red line around this. That's the posterior covariance over this function value. And this gives us an error bar, an uncertainty over the value of this integral. And I've plotted this uncertainty as well. That's the dashed line up here. And you can see that sort of initially it's perhaps somehow useful, but then it's actually a really bad error bar. It's extremely underconfident. It's really worried that there will be a lot more complicated things going on which I haven't seen yet, and that you shouldn't really rely on your estimate yet. Why is that? Exactly. So I said I'm just going to use this GP because I like it, right? So this is this Gaussian distribution, and it produces functions which are continuous with probability 1 and non-differentiable with probability 1. It's a very, very rough kind of prior. That's not the right prior for this function, and I'm sure if I would have just shown you this black line and said, what's a good GP prior for this kind of function, nobody would have said Wiener processes, right? But if I tell you I'm using the trapezoid rule to compute an integral, you say, okay, it's good, it's none of my damn business, right? This works well. Now that I've told you that it uses this prior, you hear, but that's a really bad assumption, you shouldn't use this method. No, this is not good, this is the wrong prior, right? So what kind of prior should we use? Do I have a slide for this? Oh no, I have a summary, quick summary. So first observation is, introducing random numbers into a deterministic problem may be not a good strategy, because it is bound to converge at best statistically fast, stochastically fast. Then I told you sort of a generic recipe for building a probabilistic numerical method, and that's to choose a model and then choose an action rule for how you compute. So decide what you're going to see, what you think you want to compute, and how you're going to decide what things to compute. And then it turns out that certain classic numerical methods, which are perhaps not the state of the art, but they're interesting, can be derived entirely from an inference perspective without having to look sort of at the old textbooks, right? One example is the trapezoid rule, which is a maximum a posteriori estimate under Wiener process prior on the integrand where regular node placement arises from information greediness. Okay, so however, doing this does not ensure yet that this posterior distribution means anything, right? So I just came up with a completely useless prior, basically. Well, it was really useful because it's a lot better than Monte Carlo, but it's not encoding much that I know about this function. It's only encoding that I know that the function is continuous, right? But this function is not just continuous. It's also infinitely often differentiable, for once. It's also strictly positive, all sorts of interesting things. And we know that it's upper bounded by this function, right? So by this Gaussian function. So let's first use just the smoothness, because that's already quite helpful, right? Just knowing that the function is often differentiable is a good thing. So here is everyone's other favorite Gaussian process, the one with a Gaussian prior. So, a Gaussian kernel, So that's this kernel that Neil mentioned as sort of really dangerous and making lots of crazy assumptions, which is true. but in this case, it's actually a relatively good assumption. It's assuming that this function that we're trying to integrate is infinitely often differentiable. In fact, it's assuming a little bit more. It's also assuming that it has a Fourier transform which exists, and the Fourier power spectrum decays doubly exponentially fast, so it's a very smooth kind of function, which is approximately true for this black line. So now I can do the exact same thing as in the trapezoid rule, just that it doesn't really have a name anymore as far as I know. Right? So we're going to ask, where should I evaluate this? Well, it turns out, again, after a little bit of thinking, you discover that you have to evaluate on a regular grid. And if you do this, you get this kind of convergence, which initially is just like basically like the trapezoid rule. And the reason for this kind of curve here is some sort of local structure in this function. But once you sort of have a relatively dense covering of this space, you get a convergence which is a lot faster again than this trapezoid rule. And this is the uncertainty estimate. So it's not particularly perfect, right? But it's better than this red line up here. It's already a little bit closer. Yes?
So, something is here you're aiming to gain most information about the function. But in fact, what you want is most information about the integral.
Yeah, and in this case, for stationary covariance functions, this is like approximately the same thing.
Okay.
So yeah, for generic covariance functions, this is more complicated. And then you have to think about how expensive it is to do this right.
But wouldn't you want to put more points where the function
Yeah.
is valid?
And I'll get back to that in a second. Yeah. So for the moment, I've only encoded that this function is smooth. I'm still thinking it's stationary. I still don't know where it's high and where it's low. Okay? But it's still converging a lot better. So if I wanted to have 10 to the minus 7 precision, I'd be done after less than 100 points rather than about 1,000 points, which is still a lot better than this red curve, right? Okay. So that's simple takeaway number 2, right? You just by realizing that the numerical method you're using implicitly makes prior assumptions about the task you're trying to solve, you might be able to suggest improvements just by encoding information that you actually patently have about your problem. And note that this is quite different from the kind of problem we have in sort of physical statistics, right? So Zubin had to talk a lot with you about priors. Basically, you kept him busy for half an hour talking about priors and why you can make all these prior assumptions and why not and so on. Because in the physical world, you basically have to have a philosophical argument over whether certain prior assumptions are acceptable or not. Here it's a lot easier because I've written down the entire problem. This is a formal language which specifies the problem totally. There's no uncertainty about what this problem is. So for example, I can tell you this function is infinitely often differentiable. And you can't question that. Well, you can, but it would be silly, right? So in this sense, actually, I think numerical problems are a lot nicer than physical inference because they are so clear, because the problems are specified in a formal language. By the way, they're not just specified to us in a formal language. They're specified to this machine in a formal language. So maybe you don't even have to do this yourself, right? Maybe the machine can figure out what assumptions it can make. Just let that sort of sink into your head. It hasn't actually been done yet, so maybe. Okay, good. So, of course, this only works, let me just quickly do this, if the prior, maybe this is your question anyway, if the prior assumptions are actually valid. So, if the prior assumptions are not valid, you can't trust this method to work anymore. So, here's an example, I'll get back to you in a second. Here's a function which is a lot rougher than the one that I just showed. And this function actually happens to be a draw from a Wiener process. So I've created sort of the optimal integration problem for the trapezoid rule, in some sense. Well, one of them. Right? And now we're going to integrate this function, again, with these 3 rules that I just sort of constructed. Monte Carlo, trapezoid rule, and this kind of Gaussian process with Gaussian kernel regression. Right? Notice again, this is not a random function now that I start the problem. Right? I produced it in a random way. I drew it using some random numbers. But now that it's up there, it's not going to change anymore. It's deterministic. It's just this curve, right? OK, so again, if I use Monte Carlo, nothing is going to change because Monte Carlo fundamentally, because it uses random numbers, has this 1 over square root convergence. And that's not going to change. So it still converges like before. If you use this trapezoid rule, then you now get a mean estimate, which is the thick line, which converges like 1 over n. Not like 1 over n squared. And that's exactly the right thing for this prior uncertainty, because if you really know that your function is not differentiable, then you don't get sort of benefits from linearly interpolating a function which has a Taylor expansion that has more than just one term, right? So then this uncertainty drops exactly in the right way, and we have a perfectly calibrated uncertainty estimate in some sense. Of course, we just got lucky because we knew exactly that this would fit, right? And if I use this smooth Gaussian process prior, then I get a really bad kind of behavior. This green line up here, that's the mean estimate. And it goes down initially actually not so bad, but then it becomes really unstable. And if I would have continued this over here, it actually rises again higher than to higher values than even the Monte Carlo estimate. And the uncertainty estimate drops extremely quickly. Sort of it diverges here and just becomes way too confident. So now this machine is sort of overconfident about its computation. Right? Your question?
So for the last line, you have this green line,
Yeah.
and you told us that the red line is like 1 over n squared, right?
Yeah.
Do you have any
No.
bound on the green line?
No, so if this were a perfect sample from this prior, then it would converge super polynomially fast. So it wouldn't be a straight line in this plot. But this function is not a draw from this prior, so I can't tell you exactly how it's going to converge. In fact, the domain where you reach this kind of convergence behavior would be somewhere over here, where we are beyond the numerical precision of this machine, and you don't really see anything anymore. Yeah?
You've also drawn the points on a regular grid on that plot.
Yeah.
Is that really what you need to do to get like the best estimate for the variance there? Because it seems to me that it would depend on the function that you...
Yes. So this is under the assumption that I've made this prior assumption. I'm not going to change it. I've decided I'm going to use this particular Gaussian process prior, and my design rule is I use this Gaussian process prior, and I evaluate in such a way that it minimizes posterior uncertainty. Now, as Neil pointed out, the posterior uncertainty of a Gaussian process is actually independent of the data points you give it. It just depends on where you've evaluated, not what you've seen. Right? So that's bad, because it gives us this kind of behavior, and now we're basically just constructing an uncertainty estimate which is not tested. Right? So we can't rely on this being meaningful unless we know that certain prior assumptions are valid. So for example, going back to the red line, which is also a Gaussian process estimate, I can actually make a strict statement that this uncertainty estimate is asymptotically underconfident because this function is so regular. So there you can make a strict statement that this line will eventually be far above the red line. Right? In the green case, you can't, because this is making a lot stronger assumptions about the Fourier transform of this function, which I haven't checked, so I don't know whether they are trustable or not. And now your next question is, well, but what if I don't trust this? What do I do? But there's a question from the other room.
Yes, the question is, Zubin mentioned something about even if you have a bad prior, you would be able to predict what's going to happen.
Yeah, let me stop you right there.
Zubin sample, and you mentioned if we evaluate a lot, we're going to get an error which increases.
Yes. So if you listen carefully to Zubin, he said, if there are finitely many parameters, comma, then eventually the likelihood will drown out. And then he conveniently stopped talking. He actually said, in the non-parametric case, it's more complicated. And that's the result. In the non-parametric case, it's much more complicated. Another thing he didn't say is that the posterior distribution is well calibrated. He didn't say this posterior distribution puts mass, evolves as you get more data points in such a way that the true answer is always somehow in a region where the posterior puts high mass. Right? He didn't say anything about the Bayesian asymptotic properties of Bayesian inference. He said something about the frequentist properties of Bayesian inference. Right? He said the mean estimate converges in a meaningful way. And this is true for both of these functions. So actually, is Arthur here? Is he sitting next door? I think he's sitting next door. Maybe you can ask him next week when he's talking about kernel methods. Maybe he'll point out that this green function here, this object, this is called a universal kernel, or a characteristic kernel. And Arthur will explain to you maybe what this means. Among other things, it means that as the number of samples increases towards infinity, eventually this estimate will be correct. It'll be consistent. Is that helpful for us? No, because you're not going to run your method forever. Right? At best, you're going to run it as long as you run your Monte Carlo sampler up here. Right? So asymptotics are not particularly interesting for numerical problems.
So in the division example you had in the beginning, we know that it's logically impossible to have an error. Here you have sort of the hack error T,
Yeah.
but you don't actually have something that was typically randomly generated.
Yes.
You could still, like...
You can still be really wrong.
Yeah.
And we'll discover more and more of these cases where we will have to make certain prior assumptions that are perhaps better motivated than using a classic numerical method. So in this case, right, you could make an argument that this green line is better motivated than the red line. It's not a hard mathematical proof, but it's it makes sense, this kind of argument, right? And that's the state we're currently in. So all of this that I'm talking about in this kind of, well, apart from the insight that this red curve corresponds to a certain Gaussian process prior, is anything between 10 to 3 years old, right? So we're still struggling very much to understand what kind of statements we're allowed to make and even make sense and what we're even looking for. So there's a very small group of people, I'll talk about this a little bit at the end, at the moment, a sort of a micro community, a cottage industry of people trying to understand these methods. And these are the kind of statements we can currently make. In fact, actually, I might have on a later slide, I'll have citations to certain slightly more theoretical papers which make slightly more statistical statements about their estimators. For example, about unbiasedness.
It was interesting because on one of the slides on the trapezoid rule, the function was actually quite often outside the error bound.
Yes, so there is something that I haven't mentioned, but I'll come back to in about half an hour, and that's that I had to draw sort of several of these red lines, and I didn't know which one is the right one, because there is actually a univariate degree of freedom in this problem. If I multiplied this kernel with a constant positive number, then these sort of lines up here would scale up and down, as Zubin said yesterday, and this would all be valid posterior error estimates in the sense that they produce the same posterior mean estimate. So just by trying to match a classic numerical method, we're still there's still a whole degree of freedom of how uncertain we should be. Calibrating this uncertainty is going to be a complicated task. You have a question as well? Good. Okay. So yes, so let's get back to this problem, right? So if our prior assumptions are wrong, then this method is not going to work well. Can we check these prior assumptions? Of course we can. We can do it exactly the same way that people like Zubin do this with their physical data. Right? If you're collecting numbers, we can check whether these numbers make any sense under those prior assumptions. So for example, there's one way of doing this. We could ask what is under this prior, this Gaussian process prior over the function, what is the probability for these particular function values that I got to see at these locations x? What kind of numbers did I expect to see under this prior? Let's divide these two things by each other, and then this could be called a likelihood ratio or a marginal likelihood ratio, if you like. You can take the logarithm of that because it's a more convenient object to look at. And what this is for Gaussian processes something very simple. It's just a quadratic form, and it involves objects which you had to compute anyway during the computation. The predictive mean, the actual numbers you got to see, and the inverse of the kernel Gram matrix, which is this sort of nasty thing for Gaussian processes, but for some of these inference rules actually can be computed very simply, as Neil showed before, right? Sometimes you just get tridiagonal covariances if you do this right. That's the reason why you can write the trapezoid rule as just a single sum rather than a double sum. Okay, now let's call this thing R. I don't know, because I needed a character. So, and let's check this for our two problems. So this is our very smooth problem. This is our very rough problem. And there's no corresponding number for Monte Carlo because I don't know how to compute that, right? So there's only two lines, one for trapezoid, one for very smooth. For this extremely smooth function, R goes below 0, so that means that this ratio is less than 1, which means that we are sort of less surprised than we ought to be by our data points. So the function is smoother even than what the prior assumes. So that means our error estimate seems to be well calibrated. Right? We seem to have predicted well what we got to see. In the other case, now the red line essentially stays exactly at 0. That's good, especially a unit test, because I've drawn these numbers in exactly this way, so they should have a ratio of 1. Towards the end, they deviate a little bit from 0. That's because this black line here up here is actually just a bunch of numbers that I've stored on my hard drive or in my memory. It's not actually a true perfect sample from a Wiener process. But for the green curve, for this very smooth prior, right at the point where the error estimate becomes wrong, we get a very strong divergence of this kind of estimate. Right? So now we've detected that there are numbers that we really didn't expect. We expected a very smooth curve, and suddenly we got these really strong deviations. And now we know that our algorithm is not trustworthy anymore. So just to make that point, what do you do now? Well, one very simple thing is to just switch on a red lamp somewhere on some control panel and say, my artificial intelligence doesn't seem to work. Right? That's how I think these things are helpful. This is sort of a diagnostic that says you're performing an elementary computation on your CPU and it seems to be the wrong one. Okay? Question?
So on the bottom left plot, when you see that this R goes below 0, does this also allow you to count that the
So with reservations, yes. So there is one of these damped IID assumptions in here that we've already heard about several times, right? So what's implicitly going on here is I'm claiming that the function at the points that I haven't evaluated yet looks similar to the function points that I've already evaluated. So you could construct a problem, and I can tell you how this problem, here's one example of such a problem. My true function could be this plus a tiny, so x of minus x minus 0. Or x minus 1 squared divided by 3000 squared. So what this looks like is this kind of function. I've badly drawn it, right? Over here, this is like this. So now, before I actually reach this point, I don't know about this irregularity. Well, this algorithm doesn't know about it. So this kind of diagnostic is not going to tell you about this until you actually hit this point, and then you suddenly know about it, right? Now, of course, that doesn't change the fact that, again, this computer has access to this string, because I've typed it into the source code when I evaluated this integrand. So maybe there would be a way of figuring this out so that you didn't have this kind of problem.
But here, in fact, you're not doing so your numerical methods are operating on quantized numbers. And you actually can
Sorry, they're running on what kind of numbers?
on quantized numbers.
Yeah. So this thing is as well.
Position.
So I'm making the same kind of assumption that everyone does, that we're talking about results that are less precise than the machine precision of this computer anyway, far less precise.
But in theory, with the GPR framework, you could put that in the noise in the...
Yeah. So if I wanted to design a method which runs to 10 to the minus 32 or something relative precision, then I would think very hard about what happens to the far right of this plot. How often in your practical work have you worried about 10 to machine precision in your computations? Probably never, right? Well, you say, okay, sometimes you need numbers that are sort of 10 to the minus 10 precise, right? But after that, you don't really care, right? And this is 10 to the minus 10 over there, and we have an estimate that goes below 10 to the minus 10.
Is it kind of
So-
the point that you could actually contemplate it within framework?
Yeah, no, of course you could contemplate that if you wanted to. You could add a noise term and you say this is the precision and this kind of thing. My point is, in reality, we are dealing with problems where like, the reason people are using Markov chain Monte Carlo and are happy with it is that they're drawing like 1,000 samples and then they're happy with the result. So they care about the first two significant digits of their computation, right? And that's the regime, I think, where improvements are interesting to make. Even if you think about reliability on sort of IT support level agreement levels, right? And it's still 10 to the minus 6 or so. It's not 10 to the minus 30. So I think this is not particularly interesting. But it's a very important point, because often when we talk to numerical mathematicians about these ideas, the first thing they ask is, oh, but is it numerically stable? And what happens if you get close to the machine precision? And what happens if you have if your computations are incorrect by 10 to the minus 30 or something? If you don't care, this is not our problem. This is what you guys do, right? No, and that's exactly why it's important that this community thinks about these problems, because we know what we need, and these people maybe don't know what we need to some degree. Maybe because they think that the only thing to do is cross-validation, right? Also on. Okay, so this is the summary of this first kind of overview, almost philosophical part. If you have accessible prior information about your problem, which you often have in numerical tasks because you have access to the source code, then you can try to construct a tailored or custom-made numerical method which includes these kind of this accessible prior information, and doing so can sometimes drastically improve computational efficiency. Sometimes, as in I've just shown one example. Constructed example, but it's an example. There's kind of contrast to physical data sources in that we have actual access to the source code, and this can maybe be helpful. However, if you make incorrect prior assumptions, basically any bets are off. You could possibly have very catastrophic behavior. However, you can check those prior assumptions at runtime using the exact same toolbox that we're using in Bayesian machine learning all the time. You just treat the result of computations as data points. And then you check whether those data points have a distribution which you expected them to have. Okay, so that's great. I hope I've convinced you that it's interesting to think about this. So now the question is, you've now heard Zubin talk about Monte Carlo methods. Maybe you'll hear Tamara talk about Monte Carlo methods as well. Yes, thumbs up. Why is everyone still using Markov chain Monte Carlo? Are these people all stupid? It's easy. It's a black box. You don't have to deal with it. Runtime might be an interesting point. So of course I have to invert Gram matrices here. That's kind of annoying, right? Having to do that. But actually for this red curve, it turns out that this Gram matrix inversion is analytical, right? So it's not always actually more expensive. The trapezoid rule is definitely cheaper than Monte Carlo, actually, right? Because it's just summing up numbers. It doesn't get any cheaper than that. Yeah? Dimensionality. So that's actually the answer I was looking for. So everyone else can. Of course, I've shown you a one-dimensional plot, and whenever someone shows you a one-dimensional plot, you should have sort of a mental note somewhere that maybe it doesn't scale, right? So there's a reason why there are classic integration methods which aren't actually called integration methods in numerical mathematics. They're called quadrature rules because they are about sort of drawing little squares underneath your function. And then there are corresponding rules for two-dimensional input functions. They're called cubature rules. And then the literature ends. Right? Because it's very difficult to put a regular grid on a space that's more than one-dimensional. Okay? So here's the question. Okay, so there's really a problem with these inference rules, right? Because regular grids don't scale to more than maybe 2 dimensions. Does this logically imply that we should use random numbers? No. Does it logically imply that the best possible convergence rate should be 1 over the square root of the number of evaluations? No. Right? There's no geometrical argument that says in more than 3 dimensions, the best convergence rate for a regression algorithm is 1 over the square root of the number of evaluations. It's just not true. Right? So somehow, and that's not just our community, so scientific computing people, high-performance computing people are doing the same thing. And physicists, theoretical physicists also do Monte Carlo integration. So somehow, historically, the development has been, people have discovered that these classic simple grid rules do not scale beyond 2 dimensions, and then they decided, oh, we're going to use random numbers, because they somehow have nice properties. I think the reason for that is that it's easy to show properties of these random numbers. You can show asymptotic unbiasedness, you can show asymptotic convergence rates, all this kind of stuff, and you don't have to worry at all about the function you're talking about, because if you want to see this, ask me after the lecture, actually, these methods always converge on every Borel integrable function. That's really cool, right? They make basically no prior assumptions other than the one that there is an integral, which is really cool. But it also means you have to pay a price for that because your best possible convergence is the stochastical one because you've introduced random numbers. So from that perspective, it makes sense to say, well, let's just try. Maybe it's hard to prove something about more than 2-dimensional, but let's just try whether we can make it work anyway. And here is one example of this. This is a paper from NIPS last year, so that's how new this kind of stuff is. I'm somewhere sort of in the far ends of the author list here. This is work by Tom Gunther and Michael Osborne in Oxford, Roman Garnett, who's now in the States, and Steve Roberts, who's also in Oxford. This is the Wasabi algorithm for warped sequential active Bayesian integration. In the Bayesian community, people like to have these sort of speaking acronyms. And it's also essentially a Gaussian process integration rule, but it makes 2 additional assumptions, one of which is particularly, well, actually they're both not all that helpful for the modeling, but really helpful for the algorithmic structure. The first assumption is that the function, the integrand is strictly positive. And that's correct for all probabilistic models, because if you're integrating a probability measures are strictly positive, right? We get that by taking a GP and squaring it, because the square of any real number is a positive real number. That's called a chi-square process, but, well, a non-stationary chi-square process, but it's just a GP squared. Right? And the other thing is we encode something about the non-stationarity of this problem. So we're encoding that it's sort of not necessarily upper bounded, but that its behavior has something to do with some Gaussian distribution. That's also possible in higher dimensions, and it's actually an assumption that works quite often for Bayesian machine learning models, because typically you have a prior over your parameters, and that prior is something known, and you can just perform the inference on the likelihood and then multiply with the prior afterwards, which gives you sort of a bound on where the numbers can be non-zero. So why is this helpful? It's helpful because what you can now do is you can ask this non-stationary, strictly positive model, where should I put my evaluations? And we'll use this sort of shortcut of asking for function values that are most variant, not the ones that actually give most information. So in this case, the first evaluation would be up here. Right? So we'll evaluate there, and this is going to be the posterior distribution, the posterior mean, sorry, over this distribution. It's difficult to plot a posterior variance because it's not a GP. It's a chi-square process. So it's sort of, it doesn't actually have a Gaussian sort of hull around this. So then after that, the 2 points of highest uncertainty about function values are actually quite close to the previous two, to the previous evaluation. Why? Because we have this assumption of strict positivity. Right? So we are because we're assuming the function should sort of typically return to 0, only regions where we've already seen that there is non-zero mass become interesting. And now if you can keep doing this, you'll get more and more evaluations which produce an irregular grid, a grid that scales to more than 1 dimension, even though I'm only showing a 1D plot, such that after a while you get a reasonably good model and you get kind of a good performance like this. This is now, well, I haven't actually continued this, but this is kind of an estimate that maybe if you're happy with what your Monte Carlo method otherwise will produce, you're quite happy with this kind of number as well after 10 samples rather than, I don't know, 1 million samples or so. So now here, this is a lot more hand-wavy than what I showed before. There's no convergence proof for this thing. This construction rule for an evaluation grid doesn't have a guarantee that we'll eventually get everything right? But it just performs empirically really well. There's a little bit of theory for this. There's some archive papers that, as far as I know, haven't been published as journal papers yet because they're written by statisticians, and statisticians tend to have to wait quite long for their journal papers to get accepted. So here's the archive version of it. There's still pretty good papers, particularly this one by Chris Oates and Mark Girolami. It's possible to build a minor variation of this algorithm, minor in the sense that you condition on 2 additional assumptions, which are really easy to condition on in this GP, and then you get a method that can be shown to be asymptotically unbiased. So that's maybe something you like, right? It's maybe a particularly interesting idea. It doesn't solve every problem, but it's somehow helpful. Here are some plots. These are plots that are also in this paper, but I've reformatted them so you won't find the exact same plots, but you'll find this data in the paper. Typical machine learning plots, right? So the red line is our algorithm, the green line is Monte Carlo, and we are better than Monte Carlo. The important thing about this is that on the x-axis we have time, not function evaluations. So computation time is not the issue. You can build methods that are fast in runtime, in wall clock runtime. The issue is how to efficiently use the information that this probabilistic model gives you to actively build a good model. That's harder than to just run Monte Carlo and just wait for it to do something by tomorrow evening. Question?
What type of Monte Carlo?
So you'll have to look at the paper. There's actually, in the paper, there are several Monte Carlo methods we're comparing with, and this is one of them. This is, I think, called simple Monte Carlo. But you'll find the exact, I mean, there's the corresponding version of these plots with about 8 lines in each plot in the paper, and I left them out here because otherwise it would be too confusing. But I'll end the integration part here because there's something else I want to quickly get to in the last half hour. So the really big takeaways, this the things that I hope you'll get away from this talk, is computation is inference. If you're computing something that is analytically intractable, you're computing an estimate for something you don't know. And you can, if you want, think about this computation as machine learning, as statistical inference, as inference. You don't have to, but you can. There is a deep formal connection between basic numerical methods and basic statistical methods in the sense that one can be described as a map version of the other. It's not just some philosophical hand-waviness. It's the numbers are the same on both sides, and the computational complexity is the same on both sides. Right? Ignoring helpful prior information can drastically increase computational cost. Using the wrong prior assumption can drastically lower performance. But using black boxes, not thinking about the method you're using, might be convenient. It might save you design time, but it's not necessarily or typically not very efficient if you really have to solve a problem fast. Using this kind of insight, we, with our ideas of machine learning, might be able to help design better numerical methods, but we also might be able to build better numerical methods for ourselves, which I think is the most interesting question. Because at the moment, machine learning is already posing some of the most challenging computational problems that mankind is currently dealing with. So we shouldn't be all so embarrassed about thinking about these methods ourselves. We just have really hard problems to think about. Training a deep neural network is not a simple computational task, even though it might look simple. Okay, So in the last half hour, I'll look at one other area of numerical computations, just not necessarily because I think you should all care about ordinary differential equations, but because it'll highlight yet another interesting aspect that I think is interesting to think about or to sort of get some ideas from. So I'll talk about the problem of solving an ordinary differential equation if you know an initial value problem. What does that mean? I'm looking for a curve, x of t, so that's a single input multiple output function, a curve, right? Something that has a scalar parameter and returns several real numbers, such that this curve has a particular value at a particular initial time t0, and such that the derivative of this curve with respect to t, the elements of this x with respect to t, at every time t, satisfy this functional relation. So this is called the differential equation, and I'm sure everyone has seen this before. Okay. Quick check. What do you think? What's your favorite solver for differential equations? Hogakuta. Who has used a solver for ordinary differential equations before? Hands up. If you're, unfortunately, I don't actually know what it's called in Python, but if you're using MATLAB, do you know the string ODE45? A lot of people think that's a solver for differential equation, and ODE45 is not just any old solver, it's a particular kind of solver, it's a Runge-Kutta method. Here's how Runge-Kutta methods work. So let's say we're looking for this black curve, which is the solution, which we don't know. Right? That's the thing we don't know. But we know that the curve goes through this point at t0. That's the initial value. We assume that this is given to us. So given that we know that this curve has to go through this point, one thing we can do is we can just plug this value into this differential equation, and we can evaluate this piece of code, which is often quite cheap. And then what we get back is a number called y1. This number is, tells us what the gradient of this curve is at that point. So it's an observation. It's a data point that tells us what the gradient of this curve is at that point. We could use this data point somehow, and I'm not yet telling you how, in some way to construct a new estimate for what the true solution is. And that's going to be this yellow curve. And as it happens, it's now a straight line, but it could be something else. Right? It's just an estimate for what the true curve might be. It's obviously a bad estimate, right? But it's an estimate. So now I could use this estimate to move forward a little bit because I care about the entire curve. I shouldn't just stay around here. Right? So I'll move forward to some point called t0 plus c1. I'll make a step c1 to t0 plus c1. And I'll plug into f my estimate for what the true solution of the ODE is. And then I'll treat the number that comes out as another observation of the gradient at this point. And I'll use this observation somehow to update an estimate for what the curve is, create a new estimate forwards in time. So I'm extrapolating essentially, plug this into the curve again, into the function again, get a new observation of a gradient. And now I have a new estimate, which is this green line. And now I could say I'm done. So I've now done 3 steps forwards to time t0 plus h. And I could call this one block of my computation because that makes it simple to think about. That's all it does. It just helps me think about what's going on. So now I've made 1, 2, 3 evaluations, and I have an estimate at t0 plus h. And now what I could do is I could treat this as a new initial value and just restart the whole process. This is what Runge-Kutta methods do, but they have 2 interesting aspects that I haven't told you yet, which actually define what's going on, really. The first one is, as you maybe already have seen, is that these estimates that we are constructing, they are linear estimates. Linear in the sense that these estimates are sums, weighted sums, over the numbers that we've collected. And because they are these weighted sums, these weights can be written in this form. This is called the Butcher tableau. This is something that numerical mathematicians like to study. Well, they like to study 100 years ago. They're now far ahead of us, but 100 years ago this was interesting. Or 50 years ago, maybe. So, and there's another interesting property of Runge-Kutta methods, which makes them so interesting, and is the reason why these 2 people have their name sort of eternalized. And that's that at this point over here, it's possible to construct these weights and these locations such that at this point over here, the difference between the true solution, the black curve, and the estimate, this blue curve, at exactly this point, so this difference between the estimate and the true solution, is a polynomial in H which has a high leading order. So the constant term in this polynomial is 0, the linear term is 0, the quadratic term is 0, and then the first term that's non-zero, in this case, this particular case, is the one with h cubed. right? Now, because h is supposed to be a small step, that's a good thing, because a small number to a high polynomial power is an even smaller number. So it's better to do these kind of blocks than to just skim these blocks together, because 3 of these blocks are a lot worse than 1 of these blocks of 3 evaluations. Okay? So why is this interesting? Well, it's interesting because there's a linear extrapolation happening here. And we know in statistics how to do linear extrapolation. These are called least squares methods or Gaussian process extrapolators. So it turns out, of course, well, actually it doesn't turn out, you can just see right away that it should be possible to construct such a rule where these estimates in here, these extrapolation estimates, are not some kind of magic numbers, they're just the posterior mean of some Gaussian process, right? Because these will be weighted sums over evaluations. That was actually pointed out by various people. I think the first one that I know is John Skilling in the 90s. Sorry, I'm missing the citation for that. That should be somewhere here. Skilling, 1991, I think. However, it's not clear, well, even though Skilling doesn't actually point out that it's connected to Runge-Kutta methods, he just says you can build methods like this. But that's interesting enough. So now the big question is, well, what Gaussian process gives us the cool W's? What Gaussian process gives us this great convergence order? And it turns out there is a really interesting class of Gaussian process models that Michael Schober, a PhD student, David Duveneau, who is now in Harvard, used to be in Cambridge, and myself published last year at NIPS. It turns out that there is a class of integrated Wiener processes. It's a limit of these distributions to an improper prior, such that this thing exactly works. Basically, so there is one probability distribution such that if you perform this kind of process, so that's kind of a purely probabilistic motivation. I have a belief over a curve, I observe its gradients, I step forward to evaluate at some points that are somehow interesting in terms of information gain, I get a posterior probability distribution with a mean such that this mean is exactly equal to this Runge-Kutta estimate. And there is a probability distribution around it. It also turns out that this particular class of methods can be implemented very efficiently, which is not surprising because Runge-Kutta methods are implemented quite efficiently, and it's the same numbers, so it should be possible to compute the same numbers in an efficient way. It can be implemented as a filter, like the one you just heard about from Neil this morning, a Kalman filter. It's just a generalization of the very simple Kalman filter that Neil showed, this Wiener process. So as an integration, actually, there is a similar problem here that we've just shown equivalence between the mean estimate of some probability distribution and a certain classical method. So we've rediscovered a certain point estimate. We know that, so there's a true solution here, which is the black line. We know that there is a classic estimate, which is the green line. And we now know how to construct a family of consistent probability distributions which have the same mean, but we don't know yet how large we should estimate the error around that. Doing this requires, again, collecting some kind of interesting information while the algorithm runs. And ideally, it should collect numbers that the algorithm collects anyway, then make some kind of regularity assumptions about those numbers to calibrate your uncertainty. This is typical Bayesian model estimation, right? And it's not cross-validation, by the way, right? So cross-validation is not a good idea in numerics because by the time you've run your algorithm twice with 2 different settings, the old method is already done. And then you don't have anything to gain anymore, right? Because the other guys are already far ahead. We need to build these methods such that we are not adding much computational cost to the existing algorithm. Okay, so that's the very simple takeaway for differential equations. This is just, I've just wanted to say that this exists to talk about some applications. As an integration, there is a classic family of ODE solvers, a classic family of numerical methods, which can be interpreted as map inference in a certain classical family of statistical methods. Again, a classical method. It's not that we are inventing a new kind of machine learning method here, right? It's just a Kalman filter. It's been around for almost as long as Runge-Kutta solvers. There is a whole family of uncertain distributions for each of these solvers, which have the same point estimate, but a varying uncertainty around them. So getting this uncertainty right requires some additional computation. Ideally, of course, this should be done such that we're not adding serious computational overhead. Ideally, it should have the exact same cost as the classic method. And in some special cases, it actually turns out that that's possible to do. But I'm not going to tell you how because it's quite technical. Instead, I'm going to show you some further applications to give you a flavor for why it's interesting to do all this, right? Because, I mean, you could also say, well, he's just sort of attaching all this Bayesian lingo to something that's been around for 100 years. Why should I care about this? So here are a few things. Basically, to come up with applications for this, you just think about what you can do with a probability distribution that you can't do with a point estimate. You sort of open up a classic machine learning textbook on Bayesian inference, I don't know, Chris Bishop, David Mackay, something, and just ask, well, what are people doing with distributions? Why is that cool? What does that mean for computation? Here's one extremely simple thing. You just draw samples, and you just show them to your user. So here's a particular example. This is a problem called diffusion tensor imaging. I have absolutely no idea, basically, about the theory behind this because I'm not a medical imaging person, but my extremely layman explanation of what's going on is, so the way this data was created is, imagine there's a patient with a brain tumor which is supposed to be removed by neurosurgery, and the surgeons would like to know where the important parts of the brain are, sort of speaking very simplistically, that you don't want to cut into, right? You want to know where the axonal fibers of your neurons run. So one way to do that is to make an fMRI image of this brain. MRI allows you to not just collect these statical images, but also to measure the flow of water molecules, so the vector field in which water molecules flow in your brain. And this local flow of water molecules can be treated as a kind of Riemannian metric on this kind of domain. It sort of says where it's easy to send messages and where it's hard to send messages, right? Where the flow is high, there's probably a pathway. Where the flow is low, there's probably no pathway. And then you find the shortest path in this Riemannian manifold, which involves solving a differential equation. And each of these curves is one shortest path between 2 points in a brain. And this is sort of a representation without the animation that would be typical. Well, it's very low resolution, but it's kind of a typical idea for what you would then show to a neurosurgeon during the operation to say, well, this is kind of the part that is important. Try not to cut into this. Simplifying drastically, right? So what you can now do is you could say, well, this method I've just used, this computation to compute those numbers, is actually uncertain because it's imperfect, right? It just spent a finite amount of time trying to compute those numbers, so it's not going to be perfect. So how do I sort of communicate this to the doctor? Well, I just draw some samples and just say, this is all possible solutions. These are all equivalent, these solutions. So if you don't like some of them, you're running a risk of actually reaching something dangerous, right? It's a very, very simple thing to do. It has nothing to do with the computation. Well, it's not a computer thing, right? It's not an algorithmic improvement. It's just an interpretability improvement. It's just something to show to your user. Here's again how this works. So this is the computation. That's what I wanted to show. Yeah. So computing. So what the MRI basically gives you is some tensor called M, which defines some metric on some Riemannian manifold. Doesn't really matter what that means, right? It's none of our goddamn business. Somebody else did that for us. We just have to solve this differential equation. And then this is the differential equation, and we get these kind of estimates. So now, a next interesting question is, well, maybe it is my goddamn business what this M came from. Because maybe I'm the technician or the medical physicist who made this picture of the brain or of this flow. And of course, there's a physical process that creates this image. And as Neil said before, there's a machine that does something. There's probably some filters running, does all sorts of things. It's not telling me how it does this computation. But actually, you can ask it to some degree how precise its computation was. And it's possible, and again, I don't know how, to assign error bars to the computation of this tensor M throughout the brain. You can sort of say there was more noise over here, so I don't actually know what the flow is. Right? This is kind of a complicated part of the tissue. These are three different views of the same brain. It's not different things. This is the same thing from three different directions. So now, this is a paper from this year's MICAI. This was last year's MICAI. This is this year's MICAI. And this is all work driven mostly by Søren Hauberg and Åsa Farhagen, which are now sort of senior and junior author on these papers. And we are sort of providing a little bit of commentary, essentially, and algorithms. So what you could now do is, you could say, well, if my solver for this differential equation turns out to just be a Bayesian regression algorithm, which claims that it gets noise-free numbers from its computations. If I know that those numbers are not noise-free, I can just try to include this noise in the computation. I can tell this numerical algorithm that its inputs are already uncertain. That's the reason why I always have these little graphical models at the beginning of each section. I could just say that the variables that are coming in are already uncertain. the metric over here has a big Gaussian error. Well, actually, it's not Gaussian, and after this computation, it's certainly not Gaussian anymore, but you can approximately make it a Gaussian. And then what you get is answers that sort of incorporate the fact that you're very uncertain about certain regions. So over here, you kind of know what the flow is, and here you don't really, because you're in a region where you are quite uncertain. You could call that propagating uncertainty through a computation. Unfortunately, the word uncertainty propagation is already taken by the uncertainty quantification community, and this is slightly different to what they do because it's completely analytic. There's no random numbers here, there's no recomputation. It's one run of the algorithm returning an uncertainty in addition to a point estimate. So that's an example, and that's basically sort of my final point. This is an example of a much more general type of problem, which I think is super exciting to think about. And this picture is taken from a position paper that we just published last week in the Proceedings of the Royal Society together with Mike Osborne and Mark Girolami, trying to argue for this kind of idea. So this is a cartoon here. It's a cartoon for the generic machine learning algorithm. Not just this particular one, but a generic one. The types of methods that we've already heard about a lot. It's an agent interacting with the physical world. So here's the physical world. This is the machine, if you like. What the machine does is it builds a model for the world it's in using data. I'll tell you in a second how it does that. And then it uses this model to predict how the world is going to change around it in the future as a function of what this method is going to do with the world. It can act in the world somehow, and these actions will influence the future states of the world. Hopefully, it chooses actions such that those future states are somehow beneficial under some loss function. So how does it build this model? Well, models typically involve variables and parameters. So variables are things that you have a probability distribution over, things that you try to model in an uncertain way, and parameters, which are sort of things you don't really want to have, but you need to have them anyway to construct your model, something you optimize. So variables involve probabilistic inference, applications of Bayes' rule. So they involve integration problems, right? Because you marginalize over latent parts of your model. Parameters involve optimization problems, as Steve Boyd pointed out yesterday. Fitting, right? Once you have this model, predicting the future involves solving some form of differential equation. Maybe a linear one, maybe a nonlinear one, but somehow a differential description of your environment. And then choosing an action is essentially, it's called control, but it's essentially another optimization problem. It's just optimization intertwined with prediction, which makes it particularly hard. Right? Okay, so how do we do this? So here, a concrete example might be we're building a robot, which is, I don't know, following a ball around. You see that it has a Kinect camera, it sees this. Someone is holding up a ball, moving it around. I think you've all seen this in the lab tour, right? And you're trying to grasp this ball. So what you have to figure out is where the ball is, what your current state of the robot is, and where the ball is going to be in the next time frame so that we can decide what kind of torques or currents to send to the motors of the robot so that it moves its arm in the right way. Maybe so these are sort of pictures coming in. This might be a simple regression algorithm. For example, I don't know, a least squares regression, a Gaussian process regression algorithm, which is basically the same thing. And maybe we have really a lot of data. So a really, really large data set, so millions of data points or billions of data points, which actually happens in control quite easily because you have a very high rate of collection of information. Then this involves inverting a really large matrix. It's not even an integration problem, it's just a linear algebra problem. Inverting a really, really large matrix. Then this model has parameters. It's the kernel parameters, the width of the kernel, something like that. We have to optimize those. So what do we do with that? Well, it's none of our goddamn business. We're going to use BFGS, right? Because that's sort of everyone's favorite nonlinear optimization method, maybe with bounds. And for the big matrix inversion, I don't know, just for sake of argument, let's say we use conjugate gradients, which is sort of a classic linear solver. Then to predict, this involves a kinematic model of the robot. So we're going to use Ruan-Kuta's solvers. Actually, this might then really be ODE 4.5 because robotists like to use MATLAB, right? And then to choose actions, we use a classic controller, I don't know, some linear quadratic regulator or something. So now what's happening is we've used black boxes for each of these computations. We've just strung them together into one big pipeline. I think this happens a lot, right? And we actually do this all the time when we build big machine learning methods. So now what can happen is, well, of course, you might be worried that all these methods will make a small error because they are just making an approximate computation, and then this small error will propagate, and it might blow up, and it might become really problematic for this computation. Actually, I'm not so worried about that because the people building these methods for us, these black boxes, they are worried about this as well. So they are building methods that are quite reliable. They will do their job right. And doing so will require a certain amount of computational effort. It just takes a certain budget because these are black boxes and they just take a certain amount of computation time, and if you don't give it to them, they just don't work, right? So then what might happen is that you spend, I don't know, you spend 10% of your time on some fast approximate computation up here, which gives you a reasonably good answer, but it's actually only precise to, I don't know, 1%, so 1 in 100, 10 to the minus 2 relative error. Then you run an optimization method, which takes 30% of your computation time, and it's precise to 10 to the minus 7. And that gives an answer for a distribution over X, which you feed into the Runge-Kutta solver, and that takes the rest of your time, 60% of your computation time, and it gives an answer which is precise to machine precision. Because that's just what these methods do. They're actually really good. It's like 10 to the minus 20 precise. So then what you've just done is you just spent half of your computation time solving a problem which was extremely imprecise to begin with. And it's completely unclear whether you actually have to spend this computation time to even get anything meaningful out. Maybe if you would have stopped much, much earlier, you would have gotten just about the same kind of quality. You just don't know because you have no way of telling this black box that what you're feeding it is already quite imprecise. There's no language for it. The right language for that is a probability distribution, a probability measure that says, here's my point estimate, but actually I'm like this uncertain about it. It's somewhere there. I don't really know what the right answer is. And then this method can maybe say, with a bit of luck at the end, okay, given what you've told me to do, this is my best estimate, and I've sort of spent a little bit of time, but there's no point spending more time on this because it's not going to get any more precise than, now the source of uncertainty is the start of my computation that you've handed to me. Doing this right allows the propagation of uncertainty through computations. I've just shown you a really, really simple example of this in this medical imaging paper. It's obviously nowhere near as complicated as this. This is kind of a dream, a holy grail for this kind of field. We have definitely not completed this, and it's going to take many years to get to this point, but it's kind of a guiding principle. Doing this, building gray boxes which take in probability distributions and return probability distributions, turns this picture, this cartoon picture, into something meaningful, into a graphical model, a factor graph. And the computations become message passing on this factor graph. And once you have that, of course, you can try to control this flow of information and use your computational resources efficiently, and you can try to detect errors in your computation so that you can rely on this agent behaving a little bit more. So with that, I'm done and just in time for today. So the summary is, you can interpret, I'll say it again, computation as an active form of inference, as collecting data to estimate a latent quantity. That's not just a philosophical observation. It's actually possible to make this connection mathematically quite precise by pointing out that several classic numerical algorithms correspond to classic statistical models. And I've shown two examples, a particular form of Gaussian quadrature and a particular solver for differential equations, which can be interpreted as maximum a posteriori estimates under certain Gaussian priors. There'll be more areas on Monday. On Monday, I'll talk a little bit more about mathematical challenges in developing these methods and also point out more applications. Important is all computation relies on prior information. If that relation is unreliable, then the computation is unreliable, and these assumptions should be tested at runtime. Once they're calibrated, you can do cool things with these distributions, like drawing samples or trying to propagate uncertainty from one computation to the next. This is all really new. These kind of developments, these kind of ideas have sprung up over the past 3 years or so. Our first workshop in this community was at NIPS 2013. So this is all still extremely new. There'll hopefully be another workshop this year. We'll see. There's a community website called probabilisticnumerics.org where you can find more papers about these kind of ideas. As I said, there's this very recent position paper which kind of outlines many of these ideas. And various people in the community have taken note. Zubin has just published a state of probabilistic machine learning review paper in Nature 2 months ago, or 1 month ago, basically, and in which he sort of pointed out that this is actually a really interesting area of research. People are now beginning to notice that that's interesting, and it's actually re-emerging because people have pointed it out before, but now we are reaching a point where we can do interesting research. So it's also maybe a point where people like you might become interested to be involved. It's early enough to do something really cool with this. With that, I'm done for today. Thanks.